Welcome to Breadboarding. This is video 10 of the Breadboard video controller series, Does it run Tetris well? In video 9 we got a C version of Tetris up and running on the Nanocomp, and we managed to get it running, but it did have quite a lot of screen interference and it didn't run very fast. So in this video what we're going to be doing is looking at how we can improve that and actually get the Tetris game to run well. So first of all, let's have a quick look at what this looked like at the end of the previous video. So I'm just going to share the VGA capture device, and if I just run up Tetris here, you can see there's quite a lot of interference on the screen and it's a little bit sluggish to respond, and I can see that it's not particularly straightforward to play. But it was enough to show that the system was working well enough. But you can see the snow there. Now, what I did first of all was look to see if I could improve this using hardware. So I did work out how to blank the output to display whilst the processor was updating the video memory. And what I'll just do is to show how that looks when I enable that. So that's been enabled. I'm just going to run it up again now. And what you can see, although there is still some interference on the display, it is better. The responsiveness is no different, but you can see on some of the white lines, you can see that there are times when that's blanked out. So although it looked like a way of trying to improve things a bit, it didn't really improve it enough. And so what I was going to do is to focus at the moment on improving the software side of things first, and then perhaps in future videos, once we've upgraded the processor, then we'll look at doing this better in a hardware level. So in the previous video we summarized as next steps to improve efficiency and performance and reduce or eliminate the RAM access snow, and also to include outline shadow tetronymos to show the drop position. Now I decided not to do that at this point in time, in that the performance of the game was just about playable by the time I finished. I didn't really want to complicate matters by adding these sort of white outline tetronymos. So to start with, what we're going to be looking at is only updating the screen when required rather than doing a full refresh. So if you remember, the ncurses library that was used for this C code basically is a library that will only update areas of a terminal screen when asked to refresh, because it maintains an image of the data in RAM and then only outputs the updates that are necessary to make the image in RAM to be the same in the display. Now in the Nanocomp we're not doing that, so we need to be a little bit more efficient there. I did also profile some of the hot areas of the application by monitoring the address lines and seeing where the hot areas were. It wasn't actually as useful as I thought it was going to be, so really until we have optimized the code first, I'm not really going to look at that. And then as part of the programming effort, we're also going to then look at reducing or eliminating this video RAM access snow. So I've actually started to use VS Code, which I found to be quite useful for doing this work. There are a few areas where the assembly language for the CMOC language is not familiar with that, so I haven't really bothered to work out how to disable that. But you can see over here on the right that the assembly language is not interpreted properly, but I don't really think that's a big issue. So what I'm going to do is to show you some of the key changes that we've made to this code to make it work better, and probably the easiest way to do that is through WinMerge. I'm just going to go through the main changes in the source code. So what I'm doing here is comparing the current source I'm working on with the source that's uploaded in GitHub under the version 1 of the Tetris code. So we're going to be looking here at the main file, Nanocomp C, which has some of the Nanocomp specific routines. We won't look at ncurses, there were just a few updates there to improve the efficiency of the clear window function. Most of the changes are in the Tetris C game logic. And as we said previously, what we're mainly doing is doing updates so that in the main game loop we don't do any unnecessary updates or any unnecessary processing, which was okay using the ncurses mechanism because it would only refresh the display when the refresh methods were being called. But in our particular case now, we're going to be writing directly to the display. So let's look at the main class first of all. So what we've got here in the display board function, we're only updating the board when the refresh board flag is set to true. Now to start with, initialize it to be true, but once we process this, we'll change it to be false. So it means each time we go around the game loop, we won't unnecessarily update the display. And as well in here, what we're also doing is we've replaced a macro that used two specific C functions to write the character, and it's now calling an assembly language optimized function and for the adding the block and also for clearing the block that we'll have a look at a little bit later. You can see here that at the end of that refresh board function, we're now turning that flag off so that we don't process this again unless some of the code further on down says that we need to refresh the display. So in particular, when we lose a row off the bottom of the board, we need to refresh the display. You can see in the display piece here as well, display piece will only be called when the flags are set. And you can see here we're also got the optimized add block and waiting for the screen blank before we call it. And you can see in the score similarly, we're only refreshing the score when the flag is set, and we've got the necessary screen waits so we don't update things, and then we're clearing the flag afterwards. So I did the change that I mentioned last time, change character generator ROM to RAM because we're actually updating the RAM. We now disable the cursor. This code here is now initializing the seeding the random number generator. So what we do is we're still setting it at the default value I had in the previous game. What we now do is wait in a loop for a character to be pressed, and we increase the random seed value. So at least it should mean that each time we run the game, we should get a different sequence of tetronymos. And then we just clearing the screen and putting titles in for the hold and next windows. We slightly changed the board layout. In particular, score needed to be a bit wider because the highest score I managed to get was about 30,000 and it overflowed the window dimensions. Now the main loop that runs here and the main thing that does all the processing is tgtick. What we do now is we pass in the windows here, particularly the main board window in, and that means that the functions below this can now update the screen directly rather than just updating the memory representation in the TG object, and then it required the display board function then to take that memory representation and output it to the display. And you can see here that the next and the hold windows are only updated there when their respective flags are set. The delay here controls how much time we have between polling the keyboard and moving the tetronymo. If we make this too short, then it tends to flash a bit too much. If we make this value too short here or too long, then it changes the responsiveness of the application. So you can see here at the end of the suspend function, so when we suspend the game, it overwrites the game was suspended, and so we need to refresh the board when we continue from suspend. And you can also see that I changed the key for the hold, so that used to be 5 and now changed it to 2, and the down key has also changed from 4 to 1. I found that when I was using it, I kept on hitting the down key when I didn't mean to, so I've moved that an extra key further away. So there's a few little tweaks like that, and there's quite a few debug messages included in there as I was going through, so I've just commented those out for now. And then at the end, all we're doing is making sure that we're waiting for screen blanks. If we put too much text in one go, then it causes the overspill and we start to get the screen noise. So you just need to break the messages up a little. Okay, so that's all the changes in that one. If we have a look in the Nanocomp C, the main changes we got here are we got these two new functions to add a block, and you can see here that we've actually hard coded the tetronymo left and right graphic images, and the code here really does the lookup of the coordinates, calculates the X address, is a bit faster than the routines it was using otherwise. And you see here similarly we've now got clear block loads of space, and then write to following locations, character locations after that. So those are the main changes we got here. There were a few other helper routines, I think. So the nanocomp wait for screen blank init. This routine also initializes the PIA ports, whereas this wait for screen blank, the faster one here, all this does is assumes the ports are already set up, and it only uses this number of instructions, so it should be a lot faster. So this should return when there's an available blanking period much sooner than the full function does. So they changed the nanocomp. So the main changes really were in the Tetris function itself. So I just moved some of the definitions around so that some of the code that was moved into here would work. You can see here the gravity level. What I have done is overridden the gravity level here to be 0, so the fastest level, just so I could show it to you a little bit later to see how fast it can go at the highest level. I may also think of adding a key to increase the level so you can speed things up if you find it too slow. So use the CFlow utility, which is a fairly standard utility available on most Unixes. So CFlow with the C files there and this Tetris graph just gives a decomposition of all the calls going between all the levels. You can see here the TG put and TG remove are where a lot of the screen updates are occurring, and so really this is how I was looking at seeing where I needed to focus on making the changes. So the TG put here is like the standard one, which you can see here, this is the original one. What I have done here, I've now got two versions. An internal one that doesn't do anything to display and just does the internal memory grid, whereas this also includes the functions to move the current row and column on the display, wait for a blanking period, and then add a block. Similar function for TG remove. Again, the original TG remove is now called internal, so it doesn't do the screen updating, and the main function there includes moving to the right location, wait for a blanking period, and then clear the block. So what this means is wherever we're doing TG remove and TG put, then they will automatically update the display. And what that means is we don't actually have to keep on refreshing the whole board every time we do most of the changes. The only time we really have to make those sort of changes is when we shuffle the lines down on the display. So the gravity tick is where the main game loop causes the tetronymos to fall. And again, what we've done here is we've started to optimize things. We're only going to do this processing if the tetronymo is moved. So by default, the processing logic was done all the time, even when with the gravity value set at any value other than 0 means that the tetronymo only moves down after n of the loops. So what this now means is that when the tetronymo is not moving, then we don't do unnecessary work. And what this does is effectively, first of all, removes it, decides what to do with it, and then puts it back again. Then the move function, the main move function, is the one that decides whether to move it left or right. And again, this now will wait for a blanking period, removes the current character, identifies that it moves, move it either direction, and then puts it back again. And the down and all these other functions are all very similar. Rotating, we're doing the same sort of thing, identifying that it's moved. And in this particular case, if we're holding the character or holding the tetronymo, then the refresh hold flag is set to true. So this means the hold window will get refreshed on the next game loop. And then this is the main routine controlling the move. And what we had to do here is make sure we pass in the window objects down to the lower levels so that those would have the necessary values available to be able to update the display. Then the check lines is where we do the checks for whether or not there's a full line that we need to scroll off the bottom and shuffle everything down. And again, this was being executed on every loop, and in fact we only need to worry about doing this if the tetronymo has moved. We remove the current tetronymo, then we check to see if any line is full, and then we shift the lines down if we need to. And you can see here this is really the main circumstance under running the game where we actually need to refresh the board. So if we do refresh the board when the row disappears off the bottom, but that doesn't happen that often, so it is not a big overhead. And then similarly, the score used to be updated on every cycle. And in fact, the score only needs to be updated when the lines are cleared. So again, this only runs this when one or more lines are being cleared, and then it also sets the flag for the refresh window to say, can you redraw yourself? Then finally, there's some code for the game over condition. So this is when the Tetronimo gets to the very top of the display. And because this was using the original remove and put routines, this was actually updating the Tetronimo on the display. So in fact, I created these internal versions that don't do the screen updating. So you just do the internal grid update, but not actually on the display. So this stops some of the flashing. Then the tick routine is the thing that actually calls this sort of whole thing. So this is the main controlling loop that does everything. And you can just see here that we've just added extra parameters and things to pass things down. And then finally, this is the initialization logic. And all we're doing here is setting the display, the board, hold, next and score windows to be true for the first time round. Make sure we display it the first time round. So those are the changes. A few other changes to headers and things, not very much, but that has been enough to effectively take out of some of this sort of buffering ncurses mechanism where it uses the refresh command, and now we're actually updating the display directly, and we're doing it fast enough to make it sort of challenging to play. So just going to compile. There are a few warnings, but nothing particularly important, and all we're going to do now is to load this down onto the NanoComp. So previously I'd sent the version 1, and now we're going to do the current version. Now, one of the things I have discovered on this is that the baud rate that is being used for the serial connection is only 9600 baud, which is about 1000 characters a second, and it does take quite a long time to download this 24K of Tetris program. So in one of the next videos when I'm doing some updates, I'll probably update the baud rate to 38K or even 100 plus kilobits per second. Okay, so that has now downloaded. Now we're going to have a look at the updated version of the Tetris code. So I've downloaded it onto the NanoComp. It does take about 40 or 50 seconds to do that, since there's about 24K of code now in the SREC file. So I've reset the NanoComp and I'm just going to run it up now. And the first thing we get is press S to start. It can be any key, but what this is doing is maintaining a loop which is used to initialize the seed for the random number generator. So this just means that each time we run it, then we will actually get a different sequence of Tetronimos for each game. When I was doing it with a hard-coded value in the previous version, then you were getting the same sequence of shapes on each game. So we'll press S. You'll see here we're on the lowest level here, so it's actually quite slow. What I will do is I'll make a change to allow me to show you what the highest level speed is. But you can see with the drop key we can actually make it go reasonably fast. The main issue is the outline. If we had the white outlines at the bottom, it would make this a lot easier. Sometimes I occasionally miss the row and it ends up going in the wrong place. It's a little more difficult to do it when doing it on a video capture card like this. And you can see there, so we've already got rid of 2 lines already. So the score here shows us out of 10 lines how many lines we've got left. So it doesn't count how many lines we've done, it tells me how many I've got to go to the next level. So as I said previously, we've changed the keys now from 4 and 5 for the keys for hold and for drop, and I've now changed that to be 1 and 2 because I found I was pressing the 4 key too often by mistake. It was messing up my games. So this is fairly slow at this level. I could speed this up a little if I wanted to, and I may add a speed up key perhaps to allow you to go up a level so that you can increase the game speed if you want to, but I'll leave that for another day. Here we've got another full, and we can also then use the hold button, so that having one of the eye shapes is quite a useful shape to have in your hold window there. So you can see here that it looks a lot better than it did before. There's virtually no snow on routine operations of the game. Occasionally, when a row clears, you with a large number of rows, you might occasionally get a little bit of disturbance, but it's an awful lot better than the previous version of the things. I think we'll swap out our eye shape here and put that down there, and we'll put that in here. We'll just try and get this last shape. That should hopefully, if I get it in the right place. There we go. So we've done 4 lines, just need one more to get. Let's just do a few more, and then we'll hopefully be able to finish this with going up a level. We need 3 more lines to go up a level, so let's just do this here. So there we go. Just do this one here. It should hopefully, and we do. Oh, that's the one we need next. Another eye, and that will allow us to go up to the next level. And we've got one more left. There we go. So we've gone up, done 10 lines, we've gone up a level, and it will get a little bit faster now. It doesn't increase the speed that much at the moment. It only reduces the count by 1, but as I said, I will recompile this starting at the highest speed to start with, and we'll see how fast that goes. Just get this one in the right place, and then last one we'll bother with now, unless we get a nice eye in the next. We got an eye coming after this. Let's just do this here. There we go. Okay, so we cleared a number of levels there. So you can see there's very little noise on the screen now, so job done. So I was just going to show some of the logic analyzer output I had when I was doing some of the investigation here. This is output of doing a clear screen. So basically the clear screen function is just writing a space out to the whole screen. However, you can see this is the character latch values and things, and you can see these are the bit values going from the character generator RAM out to the shift register, and you can see that even though this should be outputting spaces the whole time and this should be a blank screen, you can see there's occasional glitches and things that are occurring here, and this is when I was looking into what was causing this sort of white snow effect. And in fact what you can see is these are the signals for the character read write. So this is our special video specific read write signal, which is a little shorter than the normal CPU read write. The normal CPU read write will be about 500 nanoseconds wide, and because of the changes we made in the previous video, this is only about 240, 250 nanoseconds. But you can see that the writing here coincides with the character latch value, and what that appears to do is that you get these stray values being picked up on the display when the CPU read write overlaps with one of the low signals for the character latch. And in fact, you'll see that there can be further updates here, and that if these don't overlap in the same sort of way, so you can see this one here doesn't overlap with here, and so you don't get the interference. Now, the part of the problem is the CPU is running on a 4 megahertz clock, and this clock cycle here is actually a 3 megahertz. And so what happens is the period here and the period here goes in and out of phase as the thing carries on. So there were 2 or 3 options I had here. One is, well, I could actually clock the CPU with the slightly slower 3 megahertz clock here, and it means that the periods would at least coincide and they wouldn't shift from cycle to cycle. And what I thought in the end, though, is that I'll leave it as is, the software solution. When I put a faster CPU in here, what we might be able to do is to run the CPU at 2 times 3.1 megahertz, and that way the CPU will be synchronized with the display, but it will be running faster than it is at the moment. So I could run it at 8 megahertz, but then I might have the same problem. So future video, we're going to look at this timing and how to get the CPU in sync with the video here. That the main problem we have with the 4 megahertz clock for the CPU is we can only extend the CPU cycle in fractions of 4 megahertz, which is 250 nanoseconds, and the problem is the gap between these things here is 320 nanoseconds. The period here is 250. So the problem is, even if we extended by a full clock cycle, it would extend it by at least 250 nanoseconds, and so we would actually end up having the same problem later on. So if we've got a faster clock cycle for the CPU, particularly at 8 megahertz, we only need this to be 125 nanoseconds, and so we should find it a lot easier to interlace the CPU updates with the video character latch and color latch signals, which cause problems. So what I've done now is I have reduced the gravity value for the first level to be the fastest that it gets to, just so we can see what this looks like. So I've reset the Nanocomp. I'm just going to run this updated version now. We'll press start. You should be able to see the sort of speed that this comes down, which is a bit faster than it certainly was before. Getting the stage where it get a bit more challenging to complete properly. As you can see, it becomes a little more difficult with the keypad to do as good of a job. So it can actually get to a reasonably challenging speed, certainly faster than probably I'm able to do using this keypad. And if we just make it finish. So that's it. So we've managed to show that the Tetris game can run on the Nanocomp, and by a bit of clever programming, we've been able to remove all of the screen refresh artifacts, all the snow effects and things like that. So I hope you found it interesting. If you found it useful, please hit like, and if you don't want to miss out on future videos, please hit subscribe. In the next videos, what I'm going to be doing is looking at upgrading the video card to be able to do 640 by 480 2-color graphics. And what I hope to try and do is to perhaps try and do some sort of lunar lander type game, if I can find something suitable to convert to run on a Nanocomp. Thanks for watching.